onto your calculator so it's all set and ready to go. What that does is it brings your calculator back to the default settings. So if anybody else has done anything on it, it's going to be cleared off. You're going to need these today. So today what we're going to look at is polynomial functions. So we've talked about quadratics. Okay, we've already looked at quadratics. We know that a quadratic is anything where my exponent, the highest exponent, is a 2. So if the highest exponent is a 2, it's a quadratic. A polynomial is anything above that. So quadratics can be a type of a polynomial function. Today we're going to look at powers of 3, 4, 5, 6, 7, and 8 and what their graphs look like. Okay? So before we do that, let's do a quick reminder of what does the coefficient do to my graph? Remember, the coefficient is the number in front of x squared. What does that do to my graph?
It determines if it's going up or down.
Correct. It determines if it's positive, it opens up. If it's negative, it opens down. What else does that coefficient do? Yeah.
It changes whether it's wide or thin.
Good. It also changes the width of it. Okay? So it determines my stretch factor as well. Is it skinnier or is it fatter? Okay? So it's going to determine the width of your graph as well. So it's doing two things. So what changes in my graph when I change that 3? What changes? How does the graph change? You just told me a couple of things. Opens up or opens down. Changes the width. What stays the same? What does not change? What does that 3 not change?
Still a parabola.
It's still a parabola. It does not change the basic shape. Excellent. The basic shape stays the same. There is something else that stays the same too.
The vertex.
Nice. The vertex also stays the same. So those two things do not change just because I change the 3. So if I want to change the graph and move it up or down, how do I do that? How do I shift my graph up or shift my graph down?
Either negative or positive.
Where?
And the first term.
No. If I want the whole graph to move up or the whole graph to move down.
Oh, the last term.
Yeah, I'm going to change my coefficient at the constant at the end. So it could be something like y equals 3x squared plus 2. That will move my whole graph up. Or I could do minus 5. That will move my whole graph down. So that's how we move our graph. What's really awesome about this idea of transformations is that one concept that you guys have already obviously learned, because you know this, we're doing it with every single chapter, and it's never, ever, ever going to change. I'm going to ask you the same questions all the time. So let's look at this graph and tell me what the zeros are, or the roots. What are the zeros or the roots of this graph? 0, yeah. X equals 0. The zeros or the roots are where the graph crosses the x-axis. That's 0. Excellent. What happens to my graph, or what happens to my y values as x gets larger and larger? So as I make my x values more and more and more, what happens to my y values? Well, let's take a look. Y equals 3x squared. Sometimes it's easier to look at this as a table rather than a graph. So as I increase my x values, what happens to my y values? They keep increasing forever and ever and ever and ever. I can see that by looking at my graph as well. As I move to the right, my x values are getting larger, right? This point is like the point 1, 3. This point is the point 2 a lot. So as my x values are increasing, so are my y values. That idea is called a limit. As x goes to infinity, y is also going to infinity. This is the basic idea in pre-calculus. And you will do this a lot in pre-calculus. In this course, it's going to be pretty straightforward. We're just going to look what happens as we go to infinity and negative infinity. That's it. Okay, in pre-calc and calc, you look at it as you go to all different directions in a graph. All right, what happens as x gets smaller and smaller and smaller? So what happens to my y values if I continuously decrease my x's? So they get smaller and smaller and smaller. What's happening to my y values? They're increasing again, aren't they? So as x goes to negative infinity, goes in this direction, the y values are still increasing. They go to positive infinity. And those are called our limits. What's happening on our extremes? This is an important concept, and you're going to see why in just a few minutes. When we talk about end behavior is saying what happens to the graph as x increases or decreases to either positive infinity or negative infinity. Okay, so what happens as x increases to positive infinity or negative infinity? That's what we mean by end behavior. So what you guys are going to do right now, and I'm going to give you a very short period of time to do this. It's going to be quick. We are going to graph each one of these. So we start with y equals x squared, the first one. And we're going to do this one together. So you're going to go to your calculator, y equals x squared. Now, I'm hoping you're saying to me, Mrs. Sheldon, we already know what this graph looks like. We've done it a bazillion times. Great. Go to y equals, type it in. Remember that to get an exponent, you can use the caret key right here. That's a quick, easy way of getting an exponent. And then just hit graph. Take that graph and now sketch it onto your paper. Unfortunately, you don't get to just hit a button and see it. You have to actually do a quick sketch. Just do a very quick sketch right on your paper. Make sure you have arrows at the top because this graph does in fact go on forever in both directions. And that is extremely important as well. Then you're going to tell me, as your x values get larger and larger, so start at the origin and move to your right. Trace the graph to your right. What happens to my y values? Well, they're getting larger and larger as well. They're going to infinity. Start at the origin again. Trace your graph the other direction. What's happening to my y values? Well, again, they're going bigger and bigger and bigger. They're going to infinity. Every basic parabola is going to look like that unless we reflect it. Okay? All parabolas have the same basic shape. And it looks just like that. Right now, I'm going to give you 4 minutes. That's it. To do the rest of these sketches. So you're going to sketch x to the 3rd, the 4th, the 5th, the 6th, and the 7th. We're not going to go to the 8th, I guess. Okay, so quickly get those sketched, please. And fill in your end behaviors. X to the 3rd, the 4th, the 5th, the 6th, and the 7th, please. Lucy, do you have a graphing calculator at home? Connor, do you?
Yeah.
Excellent. Hopefully about another minute, maybe 2. All right, you should be pretty close to finished. Let's take a look at these graphs. Tell me what you notice about these graphs. Hopefully you notice something. Tell me what you notice.
That the even ones are like going up and the odd ones are like weird.
So the even ones are doing the YMCA dance, right? They're both going up, both ends. Every single one of these functions that's even, all of them look kind of the same. The odds are all staying alive, right? We're going up, we're going down, we're going up, we're going down, we're staying alive. Okay, so staying alive is your odds, your evens is the YMCA dance. You need to know your basic shapes of your graphs. Okay, that's important. You need to know that even graphs look like the 2, 4, and 6. The odd graphs look like the x cubed. Okay, so as one side goes up, the other side goes down. So, as we're filling in, what happens as x goes to infinity, every single one of these evens is exactly the same. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to positive infinity. All even functions are exactly the same answers. With the odds, as x gets bigger and bigger and bigger, what's happening to y? It's going up as well. It's going to infinity. But as x gets smaller and smaller and smaller, what's happening to y? Decreases to what?
Negative infinity.
Negative infinity. There it is. So it's going to infinity and it's going to negative infinity. Okay? That's our basic shapes. Questions, comments, concerns? Let's take a look now at what the graphs look like in more detail. So we're going to start with this big one. Before we do too much, we have to know some basic information. The first question that I want to know is, what is my leading term? Let's see how much you guys remember from your algebra days. What is my leading term? What's my leading term? X to the fourth. Good. The leading term, as long as they're in order from highest to lowest in terms of my exponents, the leading term is just literally the first term. Excellent. What is the degree? Emily, what's the degree of my polynomial? It's your highest exponent. 4. Correct. This is called a fourth degree polynomial. Your degree is simply the highest exponent. The degree of the polynomial tells us the basic shape. So what does this graph look like? Okay. might go on with it, but in general, what does it look like? All fourth degree polynomials have a basic shape. They look kind of like a U, okay? They might be a little bit more flattened out in the middle, and there might be some other junk going on in the middle, but they all have the same basic shape. And the degree tells us that. The degree helps me to determine what my end behavior is going to be. So because I know this is going to look kind of like a U, I know that as x goes to infinity, y is also going to go to infinity because all evens look the same. As x goes to negative infinity, y is going to go to infinity because all even polynomials that have an even degree always look about the same. On the ends, on the extremes. Like I said, there's going to be stuff that's going to happen in the middle. We're talking about what's going on the outside. Rosalind, what's my constant on this one? What's my constant? The number that will never change no matter what my variable is. Correct. My constant is 18. It's that number that's all by itself. It's got no variable with it. What does that constant tell me? What is that constant? It's my y-intercept. It tells me where that graph is going to cross the y-axis. Excellent. We know a lot of information about this graph, and we haven't even looked at the graph yet. Okay? We have an idea of what this thing is going to look like. Excellent. So now, let's look at the graph. And we're going to find the zeros using the graphing calculator. So here we go. Graphing calculator's out. Let's go to our y equals. Clear out whatever's in there and type in your equation, please. You should be following along and doing this on your calculator. So I've got x to the fourth. Make sure you arrow out of that exponent so you don't stay up there. Minus. Do not use a negative. It's got to be a minus, guys. All right, so I'm typing in my entire equation. And now let's look at the graph. So Mrs. Sheldon said this kind of looks like a parabola. And you're probably looking at this saying, this doesn't look anything like a parabola. There's a lot of junk going on here. Let me change my window a little bit. I'm going to go negative, actually negative 10 will be okay now. Let's just change the y's for right now. I'm going to go, my y min is going to be negative 30, and my y max is going to be positive 30 for right now. So that graph doesn't look like a U. What letter does it look like? It looks a lot more like a W, doesn't it? But watch. I want to show you something real quick. I'm going to change my window again. What's it look like now? More like a U, doesn't it? Watch this. If I were to keep zooming out and get further and further and further out, not really looking at what's going on in the middle, but looking at this more just holistically. Do you see how it has that basic U shape? Yeah. And then what ends up happening is, as I really look at what's happening at my roots, that's when all of a sudden we say, hey, we can tell what's going on here. And this graph isn't a U, it's more like a W. All right, so we want to find the zeros. The zeros are where the graph crosses the x-axis. The easiest way to do so, and I'm going to do this in kind of two parts. Let me just freeze this up front real quick. We're going to go to y equals. We want to know, where does this graph cross the x-axis? So we start with this little graph, right? So it looks like this. the x-axis. I want all of these roots. So what we're going to do on our graphing calculator is we're going to say, okay, we have a graph of our quartic, something to the fourth power is called a quartic. Now go ahead and graph the x-axis. Well, the line for the x-axis is just y equals 0. Hit graph again. What's cool if you have a color calculator is you can tell that it graphed it because now my line for my x-axis is turned red. We want to find all of these points of intersection. Now, I am going to caution you, do not just eyeball it, my friends. This one happens to be the whole numbers, but that's not going to usually be the case. Okay? So, second, we want to calculate where these two graphs intersect. FYI, there is more than one way of doing this. I just find this way the fastest way. We're going to go down to number 5, intersect. So we did second, calculate, intersect. The calculator is going to ask me some questions. It says, is this the first curve? If you look up top here, you're going to see a big long equation. It's saying, is that the first curve that you want to look at? To say yes, just hit enter. Because yeah, it is. Now it's saying, is this graph right here the second curve that you want to look at? It's actually blinking on it as well. Yes, it is, so I hit enter. Now it says, make a guess. To make a guess, we're going to use our arrows to get close to one of the points of intersection. To tell the calculator that you're ready for it to calculate it, hit enter. The first point of intersection is x equals -3. So I'm going to write that right on my paper. X equals -3. Please make sure you write x equals. I cannot stress this enough. It's got to say x equals. All right, now we're going to do the same thing. We're going to find the next point of intersection. Second calc. Number 5 again. Yes, this is my first curve, so I hit enter. Yes, it's my second curve, so I hit enter. Now I'm going to get close to the next one. Hit enter again. The second point of intersection is x equals -1. We would continue doing this for the next 2 points. I'm going to tell you that it's x equals 2 and x equals 4 are the other ones. Okay, just to save a little time. So we can find our points of intersection using our graphing calculator. We just solved this parabola, or this quartic. We found the solutions without ever using any algebra. All right, try the next one. I want you right now, using your graphing calculator, to find the zeros of this function. Find the zeros of this function using the graphing calculator, please. So I'm going to type in my equation first. Making sure I use minus, not negative. That's important. Whoa, I forgot to make sure I wasn't in my exponent anymore. Make sure you arrow out of your exponent, otherwise you're going to be in trouble like I was. And then we're going to find where the graph crosses the x-axis, so also put in y equals 0, please. When you do your sketch, you're going to notice that this is a cubic Put arrows at the end because you guys know, or you should know, the basic shape of a cubic is staying alive. It's going up and it's going down on the opposite ends. And then you can go ahead and put in your 3 points. Please practice at least 1 or 2 of them, ladies and gentlemen, using the second calc feature on your calculator. Okay? Even though I know you can see the points pretty nicely using our scale, make sure that you know how to do it on the graphing calculator because you're going to need to know how to do that. And you should find 3 points of intersection on this one. Yes?
Can you teach me how to do the calculator?
Yeah. So you need to take a guess. So you've got your first 2 things, okay? So just hit enter. You're close to where the 2 graphs intersect. Right there.
Oh, so it gives you the answer.
Yep. So second calc again. So 5, right? You always just hit enter twice. Now I'm going to get close to where they intersect. Right, that was like one of the roots. Hit enter. And it'll tell you exactly what it is.
Oh.
Okay. Anybody else need help on the graphing calculator portion? Yep. You made your guess, so you're going to get close to it, but now hit enter. Now it tells you exactly what it is. That's it. Okay? All right, last one of these. Oh, man. All right. Last one. Go ahead and find the zeros for me again. And then we're going to use this information. So 2x squared minus 3x minus 4. We're going to find the roots. So again, I'm going to need that y equals 0 because I need my x-axis because I want to find out where do these 2 things cross. You should have a general idea already of what that graph looks like. It's a parabola, right? So we know it's going to be a parabola. And you should also know what the y-intercept is going to be for it. Ooh, that one's not nice. Good. So second calc, find the points of intersection, number 5. Hit enter when it says, is this your first curve? Hit enter when it says, is this your second curve? Get close to where one of the roots are. Hit enter again. I love that you got a nasty number this time. So x equals, don't forget the x equals, please, negative 0.850781. Thank you. Second calc, I make mistakes all the time, so it's nice somebody actually acknowledges that it's right. And then I'm going to get close to the second point of intersection. Whoa. Hit enter again. Whoops. And my second point of intersection is x equals 2.350781. About. Sweet. All right. Any questions so far? Let's tie this all together now. Let's do this. So we just did 3 different graphs. The first graph, the first function that we did, the f of x function. How many roots were there? Go back and look at your notes real quick. How many roots? 4. What is the degree of this polynomial? 4. Yay. Next one. How many roots did we have for the next graph? 3 roots. Across the x-axis 3 times. What's the degree of this polynomial? 3. Woo! Next one. How many roots were there? 2. What's the degree of the polynomial? 2. Woo! We talked about this when we did quadratics, right? We talked about the fact that how many solutions there were, the number of roots, was tied to the fact that it was a second degree function. We had 2 roots. Sometimes those roots were equal. Sometimes those roots were not equal. So is it always the case that the degree has to match the number of roots? Let's see. Take a look at this graph right now on your calculator, please. Y equals x squared plus 4. Y equals x squared plus 4. And I'm going to turn off the next one. I don't need that. How many zeros are there? How many times does this graph cross the x-axis?
0 times.
It never crosses the x-axis. What kind of roots does it have if it never crosses the x-axis? Imaginary. It's a negative under the radical. We have here imaginary roots. We can only dream of them. We can't actually see them. Okay? So we have imaginary roots here. The graph never touches the x-axis. We do know, however, that we can find the roots. I can say, what are the solutions to this? And this one's not horrible to do, actually. Subtract 4 from both sides. What's my next step? Take the square root. Thank you. Take the square root of both sides. Never, ever, ever forgetting that plus or minus. So x equals plus or minus 2i. So I know that my 2 solutions are x equals 2i and x equals negative 2i. My roots are imaginary. It won't actually cross the x-axis. But I have 2 roots. I have 2 solutions. Okay, I do have 2 of them. They're just not real numbers. Sometimes our roots are going to be imaginary. However, the number of zeros is always going to be whatever the degree is. So take a look at x squared plus xx plus 9 on our graphing calculator real quick. Just as another quick example. We know that when I look at this graph, it only touches the x-axis once. The only place that touches the x-axis is at negative 3. But remember what we said. This means that there's actually 2 roots. They just happen to be the same number twice. So I have 2 roots, I have 2 solutions, it's just the same number 2 times. This idea, ladies and gentlemen, is going to be so important. We talked about it with quadratics. We're going to talk about it a lot more today and the next class. So let's take a look at this one. Let's find the solutions. Let's find the real zeros. So just by looking at the graph, what are my real zeros?
0.
X equals 0. I like it.
5.
X equals 5. There they are. Excellent. X equals negative 1. Notice that I wrote x equals next to every single one of these. I look at my basic shape. My basic shape is my staying alive shape. So I know that my degree has to be odd. I have 3 roots. What do you think the degree is probably for this polynomial?
3.
Yeah, it's going to be a 3rd degree. sure that your answer makes sense. Could you say to me, well, Mrs. Sheldon, that could be a 5th degree? Yes, it could be. You're right. But it could be a 3rd degree. Okay? God bless. Let's try another one. Look at the graph to find the real zeros. All right, well, that's not too bad. Derek, tell me what my zeros are, sir. X equals -3, correct? And x equals +3. I love it. So I have 2 real solutions. I look at my general shape, and it's doing the YMCA. Correct. The YMCA dance is an even degree. This tells me that it's got to be an even degree. So if I ask you to take a guess what the degree of the polynomial is, Aaron, what are you going to tell me? What degree do you think it is?
2nd degree.
I would agree with you. Could counter argue with me and say, Mr. Sheldon, I think it's a 4th degree? Yes, you could. I'm going to go with the logic of the obvious, and we're going to go with 2nd because it looks better. All right. We are doing well. Let's continue. Okay, let's find all of our roots first. All of our roots. Nate, go.
X equals -3.
X equals -3. I like it. Keep going.
X equals -1.
Beauteous.
X equals 2.
And last one.
X equals 3.
Beautiful. What you guys are going to be doing for me the next class is we're going to write the equations of these. You just did the hardest part. That right there is the hardest part.
Really?
True. I wouldn't lie.
That's crazy.
All right. So, basic shape. It looks sort of like this. Our hands are going up on the opposite sides. We're doing the old YMCA, so I know that my degree must be even. We stay alive if we're on. Okay, so we're doing the YMCA, so it's an even. See, it's got like a V in it for even. And the arms go up like that. See? Got it? Okay. All right, so tell me, what degree do you think this polynomial is? A 4th degree? Could I argue? Connor wants to argue and say, Mrs. Sheldon, I think it's a 2nd degree. No, you would be wrong this time. Because I have 4 distinct roots. You've got to tell me it's at least a 4th degree. Now, if you want to argue it might be a 6th degree, we can get into an argument about that. Okay? But let's just go with 4. Because I have 4 real roots. It looks nice. Wonderful. All right. So, we know that a 2nd degree looks like a parabola, right? Just a nice, smooth U. We know that a 4th degree, it's got the outside that looks like the U, but there's some junk going on in the middle. So my question to you is, what about this graph that I've shown you? Is it a 2nd degree or is it a 4th degree? We know it's got to be even because it's going up on the ends, okay? It's doing the YMCA dance on the end, so it's got to be even. So my question is, let's argue if it's a 2nd degree or if it's a 4th degree. You think it's a 2nd degree? Raise your hand if you think it's a 2nd degree. I love how y'all look around and see who else. Raise your hand if you think it's a 4th degree. Who wants to argue why they think it's a 4th degree? Why do you think it's a 4th degree and not a 2nd?
Can it be both?
It cannot be both. Nope. It can't be both.
I can argue why I think it's a 2nd degree.
Why?
Because I can kind of see where you're getting the 4th degree because on the positive side of the x-axis, that you can see that it might hit twice in the same place.
Okay.
And it also hits on the left side of the x-axis, which is the negative, so that would technically be 3 points.
But we know it can't be 3, right?
Yes, because it goes up. So
Correct. So it's gotta be 2 or 4.
So it'd be 2 if you count that as the same thing.
All right. Okay. I'm following your logic. I'm catching what you're throwing down. Go ahead.
I'd say it's like second because it only changes like direction once.
Seriously?
Good answer.
I didn't know about that coming, guys. All right. So we are going out that way. Oh, number